All right, let's get straight into it. We're going to do a deep dive into a full question on the halogens from a past AQA GCSE Chemistry paper. We'll break down every single part from the simple trends right through to that big 6-mark calculation so you know exactly what the examiners are looking for.
So, here's the game plan. We're tackling question 8 piece by piece. We'll start with the basics, like states of matter, then dig into reactivity, and finish off with that challenging 6-marker at the end. Trust me, by the time we're done, you'll see exactly how to pick up every single mark.
Okay, first things first. Before you even think about writing an answer, you've got to look at the information they give you at the start of the question. It's always there for a reason.
So here it is, Table 5 from the paper. It shows the melting and boiling points for fluorine, chlorine, and bromine. You know, the first 3 halogens in group 7. These numbers right here are going to be the key to cracking the first few parts of the question.
The first part, 8.1, is a nice gentle start. Just a 1-mark question asking about the state of bromine at 2 different temperatures. This is really just a test to see if you can read and interpret the data correctly.
So how do we figure this out? Well, you just have to compare the temperatures to the data in the table. At 0 degrees C, we're above bromine's melting point of -7, but we're still below its boiling point of 59 degrees. So what does that make it? A liquid. Then, at 100 degrees C, well, it's way above its boiling point, so it's definitely turned into a gas. Boom, 1 mark in the bag.
Right, let's move on. Now we're going to build on that and start explaining the properties of the halogens. We're going from just stating what's happening to understanding the science behind why it's happening.
Okay, here we go, a 4-mark explanation question. For these bigger mark questions, you really need a structured answer to make sure you hit all the points. It's asking why the boiling points are changing as you go down the group.
And check this out. This is basically the perfect answer, laid out step by step. This is exactly what the mark scheme is looking for. You get 1 mark for just stating the trend. Boiling point goes up. A 2nd mark for linking that to the molecules getting bigger. A 3rd for talking about stronger intermolecular forces. And that final crucial mark for saying that this means you need more energy to break them apart. It's a chain of logic.
I love these kinds of questions. It's a classic little 1-marker, but it's designed to really test if you understand a fundamental concept in chemistry. It's a bit of a trick question if you're not thinking carefully.
And here's the key idea. Boiling isn't something one tiny molecule can do on its own. It's all about the energy needed to separate loads of molecules from each other. So you can't talk about the boiling point of a single molecule. It just doesn't make sense. It's what we call a bulk property, a property of the whole substance, not the individual parts. That's the key phrase the examiners love to see.
All right, a quick and easy 1-marker on safety. The paper describes an experiment where iron reacts with halogen gas. So, why the fume cupboard? And the mark scheme is pretty clear on this. You just need to say that the halogen gas is toxic. Simple as that. You could also say it's poisonous or harmful. Any of those words will get you the point. Easy mark, but super important to know. Okay, we've talked about physical properties like boiling points. Now let's switch gears and get into the chemical properties. We're going to focus on the trend in reactivity, how these elements actually behave in a chemical reaction.
Right, another explain why question, this time for 3 marks. This is a really common one. So, why do the halogens get less reactive as you go down group 7? It's all about their electron structure.
To nail these 3 marks, you have to connect the dots. First, as you go down the group, the atoms get bigger, right? So the outer shell of electrons is further away from the positive pole of the nucleus. That's point 1. Point 2, because it's further away and there's more shielding from inner electrons, the attraction from the nucleus gets weaker. And for point 3, what does that mean? It means it's harder for the atom to pull in and gain a new electron, which is how these halogens react. So an electron is gained less easily, which means the element is less reactive. Perfect.
Okay. Deep breaths, everyone. This is it. The big 6-mark calculation that you often find at the end of a question. Now, these can look pretty scary, I know, but they're just a process. If you break it down into steps, it's totally manageable. Let's walk through it together.
So what do they actually want us to do here? It's asking for 2 things. First, we need to figure out the simplest ratio of iron to chlorine atoms in the product. And second, we have to use that to write the final balanced chemical equation. It's a classic reacting masses calculation.
Okay. Here's our data. The biggest trap here is not to get thrown off by the mass of the glass tube. We don't care about the tube itself. We only need to work out the mass of the stuff that actually reacted. That's the iron and the chlorine.
All right, step 1. Let's find the mass of our reactants. To get the mass of the iron, we just take the mass of the tube with the iron, which is 56.04 grams, and subtract the mass of the empty tube, 51.56 grams. That gives us 4.48 grams of iron. Easy. Now for the chlorine. We take the final mass of the tube in the product, which is 64.56 grams, and subtract the mass of the tube and iron we started with. That gives us 8.52 grams of chlorine. Step 1, done.
Step 2 is where the chemistry really kicks in. We have to convert that mass into moles. Remember the magic formula? Moles equals mass divided by relative atomic mass, or R. For iron, the R is 56, so we do 4.48 divided by 56, which gives us 0.08 moles. For chlorine, the R is 35.5, so 8.52 divided by 35.5 gives us 0.24 moles.
Now for the ratio. This is the easy bit. You just take your 2 mole values, 0.08 and 0.24, and you divide both of them by the smallest number. In our case, the smallest is 0.08. So 0.08 divided by itself is 1, and 0.24 divided by 0.08 is 3. That gives us a beautiful, simple whole number ratio of 1 to 3.
And that 1 to 3 ratio tells us the empirical formula. For every 1 iron atom, there are 3 chlorine atoms, so FeCl3. But wait, we're not done. The question asks for the balanced equation. We have to remember that chlorine gas doesn't exist as single atoms. It hangs around in pairs, so it's Cl2. So we start with Fe plus Cl2 makes FeCl3. To get that to balance out, we end up with our final answer. 2Fe plus 3Cl2 gives you 2FeCl3, and that is how you bag all 6 marks.
So there you have it. Question 8. Completely smashed. But before you go, here's something to chew on. We've just seen that the halogens get less reactive as they get bigger because it gets harder for them to gain an electron. So what do you think that tells us about the alkali metals over in group 1? They react by losing an electron. What do you think happens to their reactivity as they get bigger? A little food for thought. Thanks for joining me.